SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon, everybody. Myself, Mr. Bikhala Ghodadra from Maharaja Siyaજરાવ University of Baroda. I am going to give a talk here on the title Sequences and Series of Functions. You can read here, it is a printing mistake. Sequences and Series of Functions. To understand this lecture, a student must have learned sequences and series of numbers and results about the sequences and series of numbers. In this lecture, we confine actually ourselves to complex valued functions, of course including the real valued, and we focus attention to the most important aspects of problems arise when limit processes are interchanged. So when we are having two limit processes, when we can interchange that and which problems arise that we want to look. We will start with certain definitions. The definition 1, that suppose fn where n is a natural number and runs over natural numbers, be a sequence of functions defined on SAT, and suppose that the sequence of numbers fnx converges for every x in E. So when you take any x in E and fn's are functions, so fnx will be just in general a complex number. We can then, so we are assuming that this sequence converges, so it will converge to some number which will depend on this x. So we can then define a function f on E by the formula that fx is equal to limit of fnx. Under this circumstances, we can say that fn converges to f on E, and that af is called limit or the limit function of fn. Sometimes we shall use the more descriptive terminology and shall say that fn converges to f pointwise on E. Similarly, we have the following definition. This is definition of convergence of a series. So if sigma fnx converges for every x in E, and if we define fx is equal to summation n is equal to 1 to infinity fx, then the function f is called the sum of this series. So what we are assuming here is that we are assuming that when you take any x in E, sigma fnx, that will be a series of numbers. So we are assuming that if that series converges, we can it will converge to some number which will depend on x, that we call fx. So in that case, f is called the sum of this particular series. This is a sigma fn means it is a series of functions. Okay. What is the main problem? Let us discuss. The main problem which arises is to determine whether important properties of functions are preserved under limit processes operations 1 and 2. Operation 1 means you have this, that fx is equal to limit of fnx for every x in E, that is pointwise limit, and 2 means fx is equal to sum of fnx, that is you have the series here. So that is first problem. For instance, which property we can look at, that if the functions fn are continuous or differentiable or integrable, is the same true for the limit function. That means if we know that each fn is continuous, for example, then can we say that the limit function or some function is continuous, or each fn is integrable or differentiable, then can we say that the same is true for the function f. What are the relations between, say, fn dash and f dash, say between the integrals of fn, or say between the integral of fn and integral of f. So that also we want to look at. What is the meaning now? That to say that f is continuous at x, what is the meaning? That it is limit t tends to x, ft is equal to fx. Hence, to ask whether the limit of a sequence of continuous functions is continuous is the same as to ask whether this limit t tends to x of limit n tends to infinity fn t equal to limit n tends to infinity of limit t tends to x fn t. So here in equation 3, here what we are having is this, that you look at the numbers fn t and first take n tends to infinity and then take t tends to x, or you again look at the numbers f and t, to first take t tends to x and then n tends to infinity. So can we interchange these two? That means can we say that this equation is true, or means if that are equal, we can say that the limit processes are in the order in which we are carried out, these processes are carried out, it is immaterial. So can we say like this? Okay. We shall now show by means of several examples that limit processes cannot in general be interchanged without affecting the result. Okay, so afterward we shall prove certain conditions in order which limit processes are carried out are immaterial. Our first example and simplest one is nothing but a double sequence. Okay, so let us look at this example. For m and n belongs to n, that is set of natural, n is the set of natural numbers, let Smn is equal to m upon m plus n. Then problem is the following. Let us evaluate. You take Smn, first take limit as m tends to infinity and then take n tends to infinity, or first take n tends to infinity then m tends to infinity. So let us we evaluate these two limits and show that they are not equal. So that is a problem. Let me recall again. Smn is m upon m plus n. We want to look at the limit when first we take m tends to infinity then n tends to infinity, and in the other way first we take n tends to infinity and then m tends to infinity. Okay, so if you look at this, for every fixed n you look at Smn and its limit as m tends to infinity, so n is fixed. So Smn, if you put the value of Smn, it is like this, it is m upon m plus n, and you can see that if you divide this numerator and denominator, अंश અને છેદને જો આપણે m વડે divide કરીએ તો here it will be 1, and here m by m, that is 1, and here it should be n by m, and now n is fixed and we are taking m tends to infinity. So this will 1 upon m will tends to 0, so this will tends to 0, so finally this will be 1 upon 1, so 1. So for every fixed n, Smn as m tends to infinity goes to 1, and therefore for every fixed n this is 1, and so we can take it is a constant sequence, you can say, because it is a 1 for every fixed n, and then what we do is we take limit as n tends to infinity, then also again it should be 1. So limit of Smn as m tends to infinity and then n tends to infinity, then it is 1. On the other hand, you look at for any fixed m, you look at n tends to infinity of Smn. So that will be limit of m upon m plus n as n tends to infinity. Now m is fixed, so denominator is nothing but m plus n, and as n tends to infinity, denominator tends to infinity, numerator remains fixed, fixed રહે છે અને denominator tends to infinity, and therefore this will go to 0 and limit 0 થશે. એટલે limit of Smn as first n tends to infinity then m tends to infinity is 0. So you can see limit the same Smn was there. First if you take m tends to infinity and then n tends to infinity, then you will have 1, but when you take n tends to infinity first and then m tends to infinity, we get 0. So these two are not equal. So we cannot interchange the limits in general without knowing anything, without affecting the result. Well, our second example is the following, that you take fn, define fnx to be like this. It is x squared upon 1 plus x squared to the power n, where x is a real number and n can start from 0, so it is 0, 1, 2 and so on. Problem is the following: show that each fn is continuous on R, but sigma fn converges to a discontinuous function. So here we want to show that a series of continuous functions, because we will show that each fn is continuous, a series of continuous function can have a discontinuous sum. That is what we are going to show. So let us see how. Observe that first of all we observe the following, that if you look at each fn x is what? It is x squared upon 1 plus x squared to the power n. What is numerator? अंशनी अंदर it is x squared which is a polynomial of degree 2, and in denominator also it is 1 plus x squared to the power n which is a polynomial of degree n, sorry 2n. So both are polynomials, and therefore fn x is defined provided denominator is not 0, and because here x is real, so x squared will always be non-negative, so denominator is not 0 anywhere, so this is defined. And of course if both the numerator and denominator are continuous functions, here both of them are continuous, so each fn is continuous, so it is very clear that it's fn because it is a rational function and denominator is not 0, and therefore it is continuous. So continuity is not a big problem. Okay, next we shall show that this series sigma n goes from 0 to infinity fn x, which is equal to n is equal to 0 to infinity x squared upon 1 plus x squared to the power whole raised to n. It is convergent for each fixed x in R. Okay, so we start with some x in R, and if that x is 0 for example, then you can see that if x is 0, the right hand side you can see that because numerator is 0, denominator is going to be 1, so the series it will be constant, each term will be constant, that is 0, so it will converge with the sum 0. Let us consider, let x be a non-zero real number. Now when x is a non-zero real number, one can see that 1 upon 1 plus x squared, it is smaller than 1 and it is greater than 0. And once you have this the geometric series which is like this, say for example n goes from 0 to infinity 1 upon 1 plus x squared to the power n, this geometric series converges and its sum is nothing but, we know that if you have a series sigma x to the power n, when 0 less than x less than 1, it converges to the sum 1 upon 1 minus x. So here our that x can be considered as 1 upon 1 plus x squared. So this will converge with this sum 1 upon 1 minus 1 upon 1 plus x square. Here x is in normal way geometric series mein the x it is this here which is the fraction. So now simplifying you get that this actually converges by taking LCM 1 plus x square and multiplying, you can see that this series will converge to this, and therefore series in 4, you can look at series in 4. Series in 4 is this, where you can take x squared away, then the remaining series is summation x squared. If you take it away, then it is n is equal to 0 to infinity 1 upon 1 plus x squared, which will converge to 1 plus x squared upon x squared. So series in 4 converges to actually x squared into this term, that is 1 plus x squared. And remember, we already know that series when x equal to 0 converges with some 0, and when x is non-zero it will converge to 1 plus x squared, and therefore we can conclude that this series sigma fn converges with some function. If we say that some function to be f, then f can be defined like this, it is fx is equal to 0 when x equal to 0, and it is 1 plus x squared when x is not equal to 0, and it is a function defined on R. Okay, we can see that remember each fn was a continuous function, that we have given already the argument that these functions are continuous. Here we have given the argument, but you can see that the sum function is fx, it is defined like this. So we can see that when you take when x is different from 0, it is 1 plus x squared. So when x goes to 0, that means when you take the limit, it is actually 1 and not 0. So limit x tends to 0 of fx is 1, which is different from 0, and 0 is nothing but the value of f0. So we can say that limit x tends to 0 of fx is different from f0, and therefore f is not continuous at 0, and therefore it is not continuous on R. Okay, so this was an example in which you can have a series of continuous functions which may have a discontinuous sum. Okay, now in this case in this next example we will take continuous functions again, and we will obtain as a limit a very strange function, a Dirichlet function, which is actually continuous nowhere, and then also the important thing that we will obtain this as a limit of continuous functions. So for example, let us see how we define. For m belongs to n and x belongs to r, let fnx is this particular limit of cos m factorial pi x this to the power 2n, and then we take limit as n tends to infinity. Here this m is fixed, x is also fixed, and pi is the normal our constant pi. Okay. So fm is obtained as a limit of these functions which are themselves are continuous functions, because cosine is continuous. So these are continuous functions on R. Now using this fn, if we will our problem is to show that limit of this fn is this function which takes value 0 when x is irrational, and which takes the value 1 as when x is irrational, and this is known as the Dirichlet function. So let us see how we can prove this. So we start with two cases, that we look at the cases when m factorial x is integer, and that is belongs to z and does not belongs to z. So if m factorial x is integer, then you can see that because m factorial into x is an integer and multiply by pi, so this will be an integer multiple of pi. So cosine of integer multiple of pi is always plus or minus 1, and so if you take its square it will be 1. So in that case fmx will be equal to 1, and if m factorial is not an integer, then cosine m factorial x cannot be plus or minus 1, and because cosine is always lies in between minus 1 and 1, so we will have a strict inequality that minus 1 less than cos m factorial pi x less than 1, of course when you have this. So this will give us that absolute value of cos squared m factorial x is less than 1, and so if you take the n power of this, which is as good as this, equal to this, because the quantity is less than 1, by a known result on sequence is that if mod x is less than 1, then x raised to n tends to 0. So if you take n power of